Hi, welcome. In this video, we'll talk about the following problem. Okay, suppose a consumer consumes two goods, X and Y, and the preferences are UXY equal to X times Y. X here is the visits to a nearby park, and Y is a composite good. Okay, the consumer's income is R, and price of the composite good is normalized to 1. Okay, so the price of Y is 1. Initially, there is an entry fee P star per park visit. Suppose the authorities are considering a proposal to reduce the per visit entry fee from P star to P prime. Okay, so we want to answer the following questions based on this particular information. So the first question is we have to figure out how much is how much will be the increase in consumer surplus due to this proposal. As we can see, there is the proposal involves reducing the price from P star to P prime of park visits. So that would naturally lead to increase in consumer surplus, and we have to figure out how much is the increase in consumer surplus from this particular proposal. Okay, the next question is suppose there is an alternative proposal to maintain the per visit entry fee at the initial level P star. So the price remains at P star, but you are handed out a cash voucher. So the consumer is handed out a cash voucher, and how much should be the minimum value of this cash voucher so that the consumer is not worse off under this alternative proposal compared to the earlier proposal. Okay, so which was to reduce the entry fee from P star to P prime. Okay, and in the next problem we have to figure out if there is a third proposal which simultaneously reduces the per visit entry fee from P star to P prime and also charges a one-off lump sum user fee. Okay, and you have to figure out what should be the maximum value of this lump sum user fee that would make the consumer not worse off under this third proposal compared to the initial situation. Okay, so here the third proposal involves reducing the price from P star to P prime, and at the same time taking off some amount of income as a user fee from this particular consumer, so that consumer achieves at least as much satisfaction level as he was achieving in the original situation, which was when the price was P star per visit, and there was no lump sum amount. Okay, no lump sum payment. Okay, and the last question is basically to compare these three amounts. So delta S is a change in the consumer surplus, which is part A. C is the solution to part C, which is basically how much money should be taken away from the consumer so that he is just as well off as he was in the original situation. Okay, so this is C, and this E is the solution to this, which is basically how much amount should be given to the consumer so that the amount is just going to give him, how much minimum amount should be given to the consumer so that the consumer is just at the original prices, so that the consumer is just as well off with this particular amount as he or she is with this proposal. Okay, so that is what we'll have to do. We'll have to compare these three amounts. Okay, so let's do this one by one. So before we begin this problem, we may have to solve the consumer's utility maximization problem and the expenditure minimization problem several times. So let us first look at what is the solution to the utility maximization problem of the consumer whose utility function is xy, and what is the solution to the expenditure minimization of the consumer expenditure minimization problem of the consumer whose utility function is uxy equal to xy. Okay. So this is utility maximization problem. you maximize the utility subject to the budget constraint. Okay, p times x plus y less than or equal to m. Here p denotes the price of x, price of y is normalized to 1. Okay, and m denotes the income. Okay, so if you solve this particular problem, okay, then the solution will have this feature that that at this point the slope of the indifference curve must be equal to the slope of the budget line, and this point must also be on the budget line. So these are the two conditions that the solution must satisfy, that marginal rate of substitution, which is y by x, is equal to the price p, price ratio p by 1. Okay, so y by x must be equal to p, and the second condition is that the point must be on the budget line, so that p times x plus y must be equal to m. Okay, so if we solve these two equations, for two unknowns, we get the demand for x and y as follows. X is going to be m by 2p and y will be m by 2. Okay, and the corresponding level of satisfaction, in optimum will be, if you plug in the demands in the utility function, you will get x times y, which is m squared by 4p. Okay, so this is basically the indifference curve corresponding to satisfaction level m squared by 4p. Okay, and this is the optimal point. Okay, and let us look at the expenditure minimization problem. So if we solve the expenditure minimization problem of this particular consumer, this is how we write the problem. Okay, that you minimize p times x plus y, subject to the constraint that xy is greater than or equal to mu, where p is positive, mu is positive are given. Okay, and again, if you see, the optimal choice will be on the lowest possible ISO expenditure curve that passes through the constraint, which is basically u equal to mu indifference curve. Okay, so this is the indifference curve where x times y equals mu. Okay, and this is the lowest possible ISO expenditure curve, and the slope of the ISO expenditure curve will be p in absolute terms, and that should be equal to the marginal rate of substitution y by x at the point where cost is minimized. Okay, or the expenditure is minimized. Okay, and it must also be the point on the indifference curve xy equal to mu. So these are the two equations that the solution must satisfy. So if we solve these two for x and y, we get the Hickson demand as x will be equal to root mu by p and y will be equal to root mu p. Okay, and what is the optimal expenditure? So basically, what is the amount spent in optimum, to achieve mu level of satisfaction? If you want to achieve mu level of satisfaction at the minimum possible expenditure, what is the level of expenditure which is required? It is given by this. So you just plug in the Hickson demand in the objective, and you will get 2 root mu p. Okay, and this is something that we'll be needing in answering those questions. So we just we can now begin answering those questions. Okay. So if you recall, the first question was find the increase in consumer surplus resulting from this proposal. So notice that the proposal is to reduce the per visit entry fee of x from p star to p prime. Okay, so this is how the situation will look. And notice that in this case the income is r. Okay, and as a result of fall in price of x from p star to p prime, this is how the situation will change. This was your original situation. This was your original budget line. This is r by p star. Okay, and the optimal choice was this point, which is r by 2 and r by 2 p star, and this is something that you can easily get by plugging in m equal to r in this expression and p equal to p star in this expression. Okay, so and this is the new situation. Okay, when the price changes from p star to p prime, this is how the new situation will look. Okay, and this is the new budget line. Okay, r by p prime is the horizontal intercept, r is the vertical intercept, and the optimal bundle is right over here. And again, to figure out this point, you can just simply plug in R and P prime in uh, in place of M and P respectively in this particular expression. Okay, so you will get that the demand for X changes from R by 2P star to R by 2P prime, and the demand for Y stays at R by 2 as a result of change in price from P star to P prime. Now, if you want to figure out the change in consumer surplus, then we need to plot the demand curve for X. Okay, we need to plot the demand curve for X, and notice that the demand curve for X is R by 2P given R. Okay, so this is R by 2P. So if we plot it in X uh, price space, this is quantity price space, then this is how the curve is going to look. Okay, it is it is decreasing in P, as you can see over here. As P goes up, the demand falls. Okay, so this is how it's going to look. And if the price falls from P star to P prime, the increase in consumer surplus will amount to this area. Okay, this is the area which is going to give you the increase in consumer surplus as a result of fall in price of X from P star to P prime. So in order to figure out this area, we just have to integrate R by 2P with respect to P from P prime to P star. So if we just integrate this, we'll get this area. Okay, and it's a simple integral. You can take R by 2 out, and then integral of 1 by P is log P, and then you simply substitute P star and P prime to get the value of the definite integral, which is log P star minus log P prime into R by 2, the whole thing into R by 2. And log P star minus log P prime can also be written as log of P star by P prime. So this is what we are going to get. Okay, and this can also be written as R into log of square root of P star by P prime, because we can take this 1 by 2 and write it as the square root of P star by P prime, inside the log. Okay, so this is delta S. Okay, so this will be the magnitude by which the consumer surplus increases if price of X falls from P star to P prime. Okay, so this is what we have found. Okay, let us do the next part, which says that how much is the value of the cash voucher, that should be provided, if instead of changing the price from P star to P prime, you are just giving enough income so that he can achieve the same level of satisfaction, at the original price. Okay, with this additional income. So this is basically here, what we need to do is, if you see, this was your original situation, this was your new situation, and now you want to give, you want to keep the price at the original level, keep the price at the original level, which was P star, and you want to just give off just enough income so that the consumer can attain this new level of satisfaction in equilibrium. Okay, so basically here you have to solve the expenditure minimization problem. So you have to solve this expenditure minimization problem, and you want to make sure that you want to achieve the level of satisfaction that you are achieving in this situation, where U is R square upon 4P prime. Okay, so you want to achieve this level of satisfaction. Okay, which is your new level of satisfaction, and you want to achieve that at the old prices. So you just want to figure out how much money is required to achieve it. Okay, and then of course, whatever is the additional money that is needed to achieve this much amount, to achieve this much level of satisfaction, is the value of E. So let us figure that out. Okay, so here you have to solve the expenditure minimization problem, and notice that the price is the original price of X, which is P star, and the target level of satisfaction is the new uh, level of satisfaction, which is r square by 4p prime. So the required expenditure is something that you're going to get by using the expenditure function that you have already calculated, which is 2 root mu p. Here you just have to substitute in place of me the target level of satisfaction, and the at and in place of p the original price p star, and you will get that the required expenditure is 2 root r square p star by 4p prime, right? Because if you just put in place of mu this particular expression, and in place of p this particular expression, you'll get this exactly this expression, and then when you simplify it, you'll get r root p star by p prime. Okay, so this is the amount of money that is needed to achieve this new level of satisfaction at the original price p star. Okay, now how much is the additional money that is needed to achieve it? So the consumer already has r. Okay, this is the amount that is needed, so the difference is the additional money that is needed to achieve this much level of satisfaction, or to achieve this particular bundle. Okay, and that is something that you will get by subtracting r from the total money that is the total expenditure that is required to achieve this much level of satisfaction. Okay, so if you just subtract this from this, you will get r into root p star by p prime minus 1. Okay. This expenditure function is something that we have already learned how to solve for the optimal expenditure. This is actually coming from here. Okay, so this is the value of E, or equivalent variation, r into root p star by p prime minus 1. Okay. Similarly, we can do the C part. So what is the C part? C part says that so if at the new prices, some amount of lump sum fee is also charged from you, so that your so what could be the maximum value of the lump sum fee that could be charged from the consumer, so that the consumer becomes indifferent between the initial situation and the new situation. So along with the fall in price, there is also a charge that the consumer has to pay, so that consumer returns to the original level of satisfaction. Okay, so that is what we'll have to figure out. So what is the maximum amount that could be charged from this particular consumer, and for that we have to again solve the expenditure minimization problem. So notice that we want to make sure that the consumer returns to the original level of satisfaction at the new set of prices. So we are going to just make sure that we solve the expenditure minimization problem at new prices, which is p prime, and our goal is to achieve the original level of satisfaction at the minimum possible cost. Okay, so this is basically our goal. This is your original level of satisfaction. Okay, and the required expenditure, in exactly the same manner, we can calculate the required expenditure using this expression 2 root mu p, where mu is this and p is this, and we are going to get r root p prime by p star. Okay, and so how much money needs to be taken away from the consumer after the price has fallen from p star to p prime, so that the consumer returns to the original level of satisfaction? It is given by the difference between this and this, which is r minus r times root p prime by p star, which is r into 1 minus root p prime by p star. And this is your compensating variation. This is the answer to part C. Okay. Now the next part requires us to compare compensating variation, which is this expression, equivalent variation, which is this expression, and the change in consumer surplus, which is this expression. Okay. So we'll have to prove that the compensating variation is less than the change in consumer surplus, which is less than the equivalent variation. So basically we'll have to prove this. Okay, and it is also given that p star is greater than p prime and r is positive. Okay, so let's prove this. Notice that we can cancel these r's. So basically, and you can call this x. I mean, it's just because it's just, let's call this x, root p star by p prime. Let's call this x. So notice that the middle expression can be written as log x after canceling the r's, of course. And this expression can be written as x minus 1, and this expression can be written as 1 minus 1 by x. So we just need to prove this, where x equals root p star by p prime, and we know that that's greater than 1 because p star is greater than p prime. Okay, so we just have to prove that this inequality holds for x greater than 1. So if we can show that this inequality holds for every x greater than 1, then we are done, right? I mean, that's all that we need to show. Okay, so let's prove this. So in order to prove this, let's look at this. So I'll tell you how we got this. So let's if you just look at this, we know that 1 by t square is less than 1 by t is less than 1 for all t greater than 1, and this is kind of obvious, right? I mean, if it's t is greater than 1, then this term will be less than 1, and this term will be even smaller because you've divided this further by t, which is greater than 1. Okay, so this inequality holds for all t greater than 1. So if we integrate, if we calculate the definite integral of these three expressions from 1 to x, then the inequality will still hold because we are integrating a function which is always smaller, than the latter one, and obviously the definite integral will also maintain the same inequality. Okay, so if we integrate it from 1 to x, 1 by t squared dt, which is less than which is of course going to be less than integral from 1 to x, 1 by t dt, and then which is going to be even less, which is going to be lesser than integral of 1 dt from 1 to x, and that's true for all x greater than 1 because this is true for all t greater than 1. So if we just integrate, we just need a definite integral from 1 to x of these three expressions, because for all t greater than 1 this inequality holds, so the definite integral will also respect the same inequality. I mean, if as long as that interval is picked from from 1 to infinity, and the lower limit is smaller than the upper limit. Okay, so as long as that's true, then this inequality also holds, okay, for the integral. So if we just do this integral, what is the integral of 1 by t squared dt from 1 to x? It is 1 minus 1 by x. What is the integral of 1 by t dt from 1 to x? It's log x. And what is the integral of 1 dt from 1 to x? That's x minus 1. And since this is true for all x greater than 1, this is also true. This is exactly the value of those integrals, so this is true for all x greater than 1. And if we now just substitute, I mean, of course we have already shown this, but if you just want to get back this term, you can just substitute in place of x root p star by p prime, okay, because that's also greater than 1, so that you can substitute it, and you will get this inequality. Okay, so that's it. Of course you have to also multiply by r this expression to get exactly this inequality. Okay, so that's a proof, I mean, that this inequality holds whenever p star is greater than p prime and r is positive. Thank you.